So, in previous lecture we discussed how in a solid the energy levels for electrons are grouped in different bands. If we again take example of sodium, that is Z is equal to 11, the configuration is 1s 2 electrons here, 2s 2 electrons here, 2p 6 electrons here, and 3s 1 electron here. So, energy levels, this 1s is almost sharply defined, 2s will be almost sharply defined, little bit of spread, 2p will also be internal, this is 1s, this is 2s, this is 2p, and then you have 3s, 3s is spread, reasonably spread, then you will have 3p and all those. Now, as far as a solid sodium of n atoms, let us say, then you have 2n electrons in as a state. So, this is 2n electrons. Here if I am writing electrons, so number of electrons 2n here, and number of quantum states also 2n here. Then in 2s also for each atom you have 2 electrons in this 2s. So, here also you have 2n electrons and you have 2n quantum states. 2p is completely filled. For each atom you have 11 electrons and 6 of them will go in this 2p. So, 6n electrons and 6n quantum states, and then you have this 3s. For each atom you have 2 quantum states in this 3s, but only 1 electron is there. So, if you have n atoms, then n electrons are there and the number of quantum states is 2n. So, this 1s band is completely filled, 2s band is completely filled, 2p band is completely filled, all quantum states are having electrons, but this 3s, this is not completely filled, this is half filled. There are 2n quantum states, but then there are only n electrons. Now, if I will be using two words very extensively, and those two words are, one is valence band and one is conduction band. So, one is valence band and other is conduction band. In this particular diagram, this band I will be calling conduction band, and this one I will be calling valence band. So, how do I qualify them or identify them? This valence band is, you start from the lowest energy band, completely filled, go up, completely filled, go up, completely filled, and then this is not completely filled. So, that last band in energy going up, so highest energy band which is completely filled will be called valence band. So, valence band I will be calling the highest energy band which is completely filled. And when I am saying completely filled, I am not taking care of any thermal interaction. In other words, I am treating this whole crystal, this whole solid to be at a very, very low temperature, close to 0 K. in thermal interactions, energies are exchanged between the lattice and the electrons and all that, and because of that energy exchange, some of the electrons may get energy and go to some other band. So, I am not taking care of that. We will talk more about this, but when I am saying here this is completely filled, this is completely filled and so on, this is for low temperatures where the thermal interactions are not taken into account. So, this is how this valence band will be defined, and next to valence band will be this conduction band, and you can write this as, you can come from top, you have other bands here also, you have other bands, you have 3s, 3p, 3d, 4s, everything is there, they are all empty. Okay. So, if I come from top, this is all empty, this is completely empty, this is completely empty, and here you have some filled, not completely filled, but some filled states. Okay. So, the last one which is not completely filled, okay, the last coming from top, the last energy band which is not completely filled, right. So, that will be called, so this is not, let me write it here, not completely filled. Okay. So, that will be called conduction band. So, we have lowest energy band, which is not completely filled. This is also not completely filled, it is completely empty, but certainly you can call it not completely filled. This is also not completely filled. So, you come down and this is that lowest energy where you have not completely filled. If you go further lower, you have completely filled band. So, this one, the first one coming from top, the first one which is not completely filled, we will call that as conduction band. So, these two words I will be using very frequently. Now, this conduction band, the name conduction band can be justified very easily, at least in this case. So, if you have this material, let us say you have some material, not necessarily sodium, you have some material which has this kind of band structure, where completely filled, completely filled, completely filled, and then partially filled. So, here you have enough number of filled states and enough number of empty states, all right. So, this kind of band structure. So, if you have this material, you can draw a wire of that, and then you can connect this material to a battery, okay, connect it to a battery. What will happen? Then you create an electric field here. Using this battery, an electric field is created here, and this electric field drives the current. That means this electric field interacts with the electrons and it tries to accelerate them, tries to give kinetic energy to them, and so this electric field is giving or trying to give some energy to the electrons. But then are electrons ready to accept that? For normal kind of situations, this energy provided by the electric field of batteries and these things is quite small. So, only a small amount of energy is trying to give. Electric field interacting with these electrons, trying to give some energy, is not going to accept energy, because if it accepts a small amount of energy, where will it go? All quantum states are completely filled, and therefore, it cannot go anywhere. So, these electrons are not going to accept that energy, these electrons are not going to accept that energy, these electrons are not going to accept that energy, because if it accepts and tries to go somewhere else at some other higher energy state, already there is an electron in that higher energy state, and Pauli exclusion principle is there. No quantum state can have more than one electrons, and therefore it cannot accommodate that. But here you have lots of empty space, empty quantum states. So if a particular electron takes up that energy and tries to goes to that quantum state with little more energy, that quantum state is available, and therefore the electron can go there, and therefore it can respond to the electric field, and therefore it can be accelerated by the electric field, it can move. So that is how these electrons are taking part in conduction, and therefore this whole band is known as conduction band. And remember, these states that I am writing, this is for the entire periodic potential, entire crystal, and therefore if the this electron occupies that particular state, its wave function is now spread over that entire area. That means the electron can be found anywhere and can go across that whole solid. So that is what we mean when we say that these are free electrons, they are free to move in the entire solid material. So those sentences are related to these. So this is why it is called conduction band, and below that you have valence band. They are all electrons, they are all attached to the nucleus, to that crystal. The wave functions are more localized and all those things. So this is how the thing happens. Okay. Now there are varieties of structures possible. One structure is this. Okay, sodium, I had taken sodium an example where there are 11 electrons per atom, and then we see that yes, you have a conduction band in which half the quantum states are empty and half the quantum states are filled at low temperature, and therefore conduction is possible. Sodium is a conductor. All metals will have this kind of property. What about magnesium? What about magnesium? Let us suppose now we consider magnesium, Mg. Here Z is equal to 12. So for each atom the configuration will be 1s2, 2s2, p6 and 3s2. And suppose I have n atoms of magnesium. So what will happen? You have those bands, and now 3s also, for each atom you have 2 electrons. That means after this splitting and all that, this also has now 2n electrons and 2n quantum states. So this is completely filled, this is completely filled, this is completely filled, this is also completely filled. Now if this is also completely filled, what you expect? If I take a magnesium ribbon and then connect the ends to a battery, try to pass a current, what will happen? The electric field will interact with electrons, and then it will try to give some energy, and this band is completely filled. So these electrons are not expected to, or you may think that these electrons will not accept kinetic energy from the electric field, and so it should be insulator, but it is not. Magnesium is a very good conductor. So what happens here? Here what happens for magnesium and in many other materials, conductors, that the next 3p state overlaps with this. This is 3s, and then next will be 3p, and after spreading 3p goes like this. Suppose this is 3p. So that means 3s and 3p, they are overlapping, and you have a single band. So you have large number of quantum states. You have so many empty quantum states, and therefore those 2n electrons which are there, they can take up energy from the electric field and populate those empty quantum states. You don't need large energy to go to this band. 3s, 3p bands overlap. So in that case, that whole combined thing will be conduction band once again. This whole combined thing will be conduction band, because this is just like one band. Once it overlaps, you have just one energy band. This is allowed, this range is allowed, this is energy gap, then this range is allowed, and this is energy gap, and then this range is allowed, and so on. So this is once again, this whole thing is the conduction band, and here is the valence band, and therefore you have enough number of empty quantum states and enough number of electrons also, and it's a good conductor. So depending on the material, the electronic configuration and all those things, you can have band structures in energy only, energy diagram only. The band structure also means the relation between the energy of the electron and the momentum vector. So that relation we are not talking at this moment. It's only one dimensional energy diagram. So you can have a situation where you have a valence band, and by definition this valence band is completely filled. Okay, so this is valence band, all these states are completely filled. And then you have conduction band, which is partially filled. So this is one kind of situation, and I remind you I am talking of low temperatures only. So this is one kind of situation where the conduction band is partially filled, partially empty. You have large number of quantum states which are filled, that means there are electrons, and you have large number of quantum states which are empty, and then you have valence band. So this is one situation. This will be conductor. Then you have another kind of material where you have valence band. By definition it is completely filled, so this is completely filled. And then you have conduction band, and this conduction band is completely empty. Okay. So this is also possible, as I defined. If you come from top, not completely filled, the first not completely filled, it's certainly not completely filled, it's not even partially filled, but certainly not completely filled. So this is the conduction band, this is the valence band. At low temperatures, 0 K, this is the kind of situation, and this energy gap is large. I'll just tell you what do I mean by large. Large means it is much larger than K times T. And when I say much large, that means, let us say, something like 100 times or 200 times, like that. 5 times, 10 times is not large. So this is one. So this kind of materials are insulators. Now let's talk about this KT business. As I told that through thermal interactions, electrons and this lattice, they keep exchanging energies, and that energy exchange is on the average of the order of this KT. So if this K into T, for example, at room temperature 300 K, this K into T is 0.026 electron volts or 26 milli electron volts. So this is KT. So this is the average, this is the order of energy exchange is of this order. But then there are interactions in which the energy exchanged is much larger than this, double of this, 5 times of this, 10 times of this, or half of this, or 1/10 of this. So that's all possible. But the probability close to this KT will be much larger. And then if I say 10 times KT, energy exchange 10 times KT, will be smaller, 100 times kT will be still smaller, 1000 times kT will be still smaller, and so on. So, if you have this kind of situation where this gap is large, let us say for example carbon in diamond form, this gap Eg is about 6 electron volts. So, compare, 10 times of this will be 0.26, 100 times will be 2.6, and this is 6, so several hundred times of this kT. It's a large gap. So, if I ask, is there a significant probability of an electron in this valence band taking up thermal energy from the lattice and moving to this? The probability is almost negligible, and therefore these electrons will stay there even at 300 K. Even at 300 K they will stay here, and this will remain completely empty, or if there are some states populated, not at all significant. So, then if you take a diamond, and connect it to a battery and apply some voltage and create some electric field, and that electric field tries to give some energy to the electrons. These are the only electrons, and other electrons are all in the lower bands. None of these electrons is ready to accept that energy, and therefore this is a good insulator, very good insulator, right. So, this is the class where you have insulators. And then the third class is you have similar structure, you have this valence band, and then you have this conduction band, and once again valence band by definition it is completely filled, but this conduction band is again completely empty at 0 K, completely empty. Okay, I am talking of low temperatures, 0 K. But this gap Eg is not very large as compared to kT. Okay, I am writing this symbol, but 10 times of this or 15 times of this or 20 times of this or even some 50 times of this is also reasonable for us, all right. So, because the number of particles are very large, 10 to the power 23 particles, so even if the probability is as low as 1 in 10 to the power 10, then also there are 10 to the power 23 particles, you will have significant number of interactions in which the energy exchange will be 10 times kT or 20 times kT or 40 times kT and so on. So, anything, let us say anything like say less than 2 eV or 3 eV is under this category. So, at room temperature or at elevated temperatures or normal working temperatures, some of these electrons here, the valence band electrons here, which are near the top of this, can accept energy through these thermal interactions and move here, all right, and they can move here. And if they move here, then you have all these empty states are there, but one electron going from here will populate this quantum state. Another electron going here will populate another quantum state. So, although the band structure is similar as it is here for insulator, but because this gap is not very large as compared to kT, at room temperatures or the normal working temperatures, some of these quantum states get occupied, and that some of this still can mean 10 to the power 13, 14, 15, 16. If the total is 10 to the power 23, some does not mean 5, 10, 5, 15 or 50. Okay, so that number is sizable. So if the electrons are here and then some empty states are created here, some empty states are created, some quantum states from which it has gone, this quantum state becomes empty. And if this becomes empty, then the some movement of electron of this energy is also now possible under electric field. If you apply an electric field, of course this can accept energy and go to a higher energy quantum state. But even here, the electrons which are in valence band, lower energy, and electric field is there. Even these electrons can feel some pinch of that electric field and can start moving in the crystal. How? This is because if this quantum state is empty and there is an electron here and the electric field is there, this electron can accept that energy and fill this. Of course, this will become empty, but some kind of electron movement is possible. So, all because of these electrons in the conduction band and because of these empty states in the valence band, both ways some electric conduction is possible if you apply this electric field, if you connect that system to a battery. Of course, the number of electrons here or the number of vacant states here is still very small as compared to this conductor case, and therefore the conductivity, electrical conductivity as compared to this case will be very, very small here, but as compared to this it is very, very large here. That is why it is called semiconductor. These kind of materials are called semiconductors. Okay, and that is what we are going to now focus. And Z is equal to 11 I have talked, Z is equal to 12 I have talked, and Z is equal to 14 is the silicon, which is the model semiconductor which I will be using for further discussions. Most of our discussions will be in reference to this Z is equal to 14 element, which is silicon. Most of the semiconductor electronics even today is built around that silicon. So, that silicon will be our model element semiconductor, which I will be talking next.